Alright, hell yeah. I'm gonna say center of mass a bunch, but what I mean is center of area. What a faux pas. Booyah. Alright, hell yeah. So in this video, we're gonna find the center of mass. And hell yeah. And center of mass has two dimensions. Because this thing is symmetric, in this dimension, the center is going to be somewhere symmetrically in the center. That's very visually to see. Now, center of mass should not be confused with, half the area being on one side and half the area being on the other. Center of mass is a leverage. And so, cool. And maybe we're just going to go for it. In this video, I'm just going to do the quickest way to get an answer. And we're going to use this equation that the center, the center of mass is going to have an x-coordinate and a y-coordinate. And so the y-coordinate is going to be this equation. We're going to have the summation of the chunks of area times their times the center of those areas. And then we're going to divide by the summation of the areas. Cool. And so let's get this. How would we draw this? What I like to do is I see that this is 120, and so this little square is 120, and we have 125 different times, and then this is 123 height. So I'm just going to do this. I'm going to go, and then I think consistently on a sheet of paper you can make dots that are fairly equal spaced apart. So we got 1, 2, 3, 4, 5 spaces, and then we're going to go down. See how that's, kind of pretty nice and square? And then booyah. So now I'm just going to kind of finish the deal. And then we can even just kind of go over here just so we're making sure we're in line. Yeah, hell yeah. Alright, so now we have our dots. Just a few more. Alright, I think we're a little bit wonky here, but okay, good enough. So now what I like to do is just do like dashed lines. I think you can do this fairly fast, and you really don't need very many dashed lines to really set for your eye to see it. For your eye to capture it. And even just kind of going lengths, it's easy to make your lines straight without too much wobble. Okay, hell yeah. That got a little bit wide, but I think we got it. And so these are going to be 120 millimeters. I'm dropping all units just for the sake of not writing a whole lot. This is 120. And then this height is 240. And just know that we have 120 here and 120 there. Okay, sweet. And then this is going to be 120 times 6, 5 times 5, sorry, 600. So this is going to be 600. Now this equation says, hey, let's divvy up these areas. Hey, that's a rectangle. I know the center of that rectangle is right there. So I'm gonna say this is y1, and we have to have a datum. You know what I mean? So you can choose anything for your datum, and that's kind of fascinating. And so this is where I will try only just to do a few minutes, and we'll talk about the theory going on here. Alright, hell yeah. And I think this is where my videos shine, and I don't want to spend too long, but even like right now I'm having an aha moment. Okay, a very simple concept is you have a beam, and what they say is like the mass is in the center. The weight of the beam is at the center of mass. And what happens is that over here you have a force of half, and then over here you have a force of half. Okay, cool. So, so here's another concept that I like. I like to think of it like this. You have a hinge, and then you have some sort of mass, and we can make this three-dimensional, so you can kind of envision that it's heavy. And this has some sort of weight, and we know that it's going to be applied right there. So your goal, so if this hinge is fixed to the ground, or to a wall or something, what you're going to have, like you have a force gun, so you have a gun that can only provide a force in this up direction equal to W, Had you had a force gun that was equal to W divided by 2, and you wanted to balance this system, well, you would put your W divided by 2 right here. And then what's going to happen is that over here, and if we see no movement, because this is a rigid structure, we have a pin, this is also going to provide a W divided by 2. And this thing is very similar to this with a roller, you know what I mean? And so you have a pin and a roller. What center of mass is saying is that, hey, you can't provide a force of W divided by 2. You have to provide the same force as this weight, and you have to put it along here some distance. And this is where I hate using variables, you know what I mean, because it trips your mind up, I swear. But anyway, so from the fundamentals is you have to apply an upward force of W. And the goal is for you to find the location where to apply this, where this thing doesn't fall, you know what I mean, because you didn't apply enough force, or you applied too much force and it starts to go. So this whole bar could spin that way, or it could spin that way, if you choose wrong. And so that's a cool, like, so whenever I look at problems that require a centroid, even if they're in like out of the page like this, what I like to do is just throw a couple hinges right here, and booyah. Is that a pretty good hinge? Anyway, so we have a couple hinges right here on a rod, and then what I'm envisioning is this is not area. You know, just make this like real thin, but then make it out of steel. And then so the very intuitive way to do these centroid problems is to envision that this is, you know, some sort of thickness of steel, and then that, check this out. This is how I double checked my answer, and this is how we'll double check our answer in the end. I'm just going to say this is made out of, where each of these squares is just 1 pound of steel. Or you could do 1 Newton if you want SI units. So then when we go, and this makes sense, because when we go back to this, it's like, hey, we're taking this total area. Like, what's that about? Well, you really want to rearrange this equation. So I'm going to rearrange this equation to look like this exact scenario we just did. So you have this, you know, this area times the center. And, you know, this is just saying area 1 times the center of 1 from this hinge. So this rectangle is area 1. The area is 5 squares. Its distance is 1, 2, 2.5 squares. Okay, that's the value for A1. So we have A1, Y1. And then we add this rectangle. We're going to have A2, Y2. So that area is 2 rectangles. The center is 1 rectangle in height. You know what I mean? Or whatever. Or just that distance in height. The side of one of these squares. And then A3... we could say it's both of these. You know, they're the same. And then we just have to know that the center of a circle is 1/3 and then 2/3, this height. So if this is the height, this center is 2/3 from this hinge. And so that's going to be area 3 times Y3. And we're going to have 2 of those. All right, and then we're just going to divide by the area total. That's A1 plus A2 plus A3. So that's that equation. So this area was A3, so 2 times A3. If I'm just saying this is A3, I got 2 of those. So that's A1 plus A2. I don't know why I'm just writing it just as sloppy. Holy hell. And I wrote 3. So 2 times A3. Booyah. So that's this equation right here. Those divided by that. All right, but let's simply rearrange this equation. What we're going to do is we're going to get this to the other side, but we're going to start here. We're going to say this is AIYI is equal to the summation of area times this center. So what we have here is that the summation, so we kind of have like the top, what the top's doing, what's the bottom's doing. So here I only have one weight, so I only have A1, Y1. That's kind of what I have synonymous with this. This area is proportional to the volume here. You know, I mean, this is where this thickness into the page is irrelevant. I'm just looking at this area, and I'm equating this area as proportional to a weight, because I know area, as long as the thickness is constant, is proportional to the volume, and volume is proportional to the weight. because volume times density is weight, and then area times thickness times density is weight. These are, the thickness is uniform throughout this area, and then the density is all the same density. It's uniform throughout. So we really just have area is proportional to weight. That's how, so that's what I'm kind of showing you, is that anytime you're doing centroid, it's really cool to think of it as a weight, or like where the area has weight. Because this definition, like this component, is the leverage of area. We're saying that I have some sort of square of area right here, and it's a distance away from this hinge, and I'm going to say that is the leverage of that area. Now even this square is made up of smaller squares, where I could say, hey, this square, the center of it's right there, and then we have this. Now it's a quarter of the area of this whole circle, and it's a little bit farther away, but this one is a quarter and it's a little bit closer. And so we still get a linear relationship where all we have to do is just take this area, find the center, and use that as our distance. Compared to some other things, like this is compared, I would compare this, because this is leverage of area, and this is a first moment, where I just have the area, and then I'm just taking a distance to it. If you have like a double leverage, or like a leverage but with the proportion squared, that's going to be like mass moment of inertia, where this is considered a first moment, where we just have area and we're multiplying it by the distance. If we had area times the distance squared, this comes up in second moment of area, well then we have the second moment of area. And it's just the fact that we took the distance squared. And that property comes out of integration, and it comes out of, this property comes out of geometry for quite a lot of places for material mechanics, where, it's not that this property is, it's unique in the fact that it's all it is geometry. It has nothing to do with the material. When we have area and a distance, it has nothing to do with the density of the material. It has nothing, so it's kind of fascinating. But what happens, especially with second moment of area, is you lose all meaning of it. Sure, we have this meaning of like an I-beam has a large number, and like a cylinder has like a solid cylinder of steel has a small number for the second moment of area. And then, you know what I mean? But because we have this squared, like different shapes can be wildly, like an I-beam can be wildly larger in number compared to other shapes. Okay, so that's going to be the second, and I would call this, it's still a leverage of area, but then that distance is being squared. So I don't know if I'm just making up a term there of like the second leverage of area or whatever. But anyway, so this is a moment of area where we have an area, some sort of distance away from something. And that area has leverage. But it's just bizarre to have area as leverage. You're like, well, what's that mean? Where here we can say that, hey, this area is actually a chunk of steel that's this thick, and it makes this steel weigh 1 pound. And so now we have the same thing. We have, we could say we have, and then let's talk about this as a vector. Because this area vector, so let's say we have our x-coordinate, our y-coordinate, and then our z-coordinate coming out of the page. So we're going to go x, y, and then z. So this area could be represented as a vector. The face of it is facing the z direction out of the page, because this is the x direction, y direction. The same thing for force. We could say that the force vector is actually acting downward. If we're going to say, like, down is gravity, so I'm going to say this force vector is acting downward. And this force has a leverage about this hinge. You know what I mean? And then this is intuitive. Like if I have a hinged, something hinged, and then I put a rod out here, and then I put a big chunk of mass on it, well, hell yeah, now that's got leverage. And if I put that same chunk of mass like right here, well, not so much leverage. And if I put a third chunk of mass right here, and if you're holding this whole system up because it's down, you know what I mean? And I say I can remove one of these masses to make your job easier because you're going to have to hold this whole system up, you know, for the next 24 hours for a contest. And but you get to choose one mass that you want me to remove. I think everyone on the whole planet, even a kindergartner, would be like, well, please remove mass number 1. Do not remove, you know, if this is mass 1, 2, and 3. You know, so that's probably the coolest part about this video right now. It's just blowing my mind. But anyway, so hell yeah. Like, just the fact that a kindergartner would be like, hell yeah, please remove this mass. And I can do this challenge for 24 hours, win that car. Okay, so that means that this mass has more power than this mass, or, you know, and not in the physics terms power, but it has more leverage, you know what I mean? So that mass is doing more, you know, from the standpoint of just like, hey, this sucks to hold up if I have to hold this stuff up. Okay, so when it comes to this, so with these masses, if I had a force, and if I could apply 3 different forces that were equal to, you know, the weight of those masses. I'm just going to put W. So now I have 3 equal forces that are lifting. So 3 people are lifting. You know what I mean? So if you had 3 people and you wanted to share the load evenly, each person would stand underneath these masses. Even though this one is like really close to this edge, still, this person would hold up. And that actually is blowing my mind too, because it seems wonky. That would be a very difficult experiment for this person to feel like they were holding up, especially with this hinge being right there. It would feel weird for them to apply that force when they would just easily be like, well, don't you have this? Like, because this person has the most leverage, but that means they're holding the most weight. But and I think I have this right, if you had 3 people equally putting the force up to hold one of these masses, you would put 1 underneath each one of those. Alright, hell yeah. And we're going to move this kind of hinge so it's just right over this mass. And again, and that really shows that this third person is kind of irrelevant. Like if this pin, you know, this pin would have to be like hella loose in its channel. But if it was, and you're like, hey, yeah, sure, this is a pin connection, but it's hella loose in its axle, this person still is lifting it up so that axle is floating. So yeah, so if you had this board with 3 masses on it, then the hinge is kind of irrelevant. Alright, so now another question from intuition. So we have this mass over the hinge, and now to win the car, we're going to have hooks in here. You know, you can hook a rope at any point along this plank, and it's going to be on a pulley. And what has happened is the contestants, they weigh a certain amount, and their weight is equal to three times this mass. And I don't even know if I'm going to mess this one up. Okay, so their weight is equal to, there's 3 masses on this plank. The plank is supported right at this hinge. They're at, and this is downward. They're asked to hook themselves to a rope on a pulley, and then carabiner into this plank with the 3 masses. And then the question is, what distance are they going to hook in? And when they hook in, if they hook in wrong, and this thing flies upward, they win no car. And then if they hook in over here and this thing drops downward, they also win no car. So now you got some skin in the game. So there's going to be a location along here where if you hook in, you get to win that car. So now let's do it from I'm going to mess up from the intuition. So that's where it's nice to use, like, so let's go back to this one. Because if I have the weight of this bar is W, and then I'm the force gun that's equal to W, well, I'm going to put my force gun right there. so that these are going to balance out, and that distance is going to be, well, if this is a length L, that distance x is going to be L divided by 2. And so this is probably the simplest one that I can think of. Now, if it comes to, yeah, so let's just do this one. Cool. So we'll use our equation. And our equation is going to look like this. So let's say this is the y direction. So this center, the center of the mass, the center of the area, center of mass and center of the area are the same, especially if your thickness is the same, and your mass, where your mass is proportional to your area. And we just said, and we're going to say weight is proportional to area, weight is proportional to mass. I think we get it. All right, booyah. So I don't need to drag my feet on this. All right, so let's try this first mass. Or let's do this one. This one is right over the axle. So we have and sorry I used M. Change all these M's to W's. You know what I mean? So we have this weight. M seems like it's mass, and mass you would have to multiply by rho to get, no, how do you get weight? Holy hell. If you have mass, yeah, you need to multiply it by mass. No, that's for volume. Let's just move on. So we have this weight 1. So we're going to call this weight 1, weight 2, weight 3. So we have... Alright, change the batteries. And I kind of have a fear of like missing out, you know what I mean? Like a fear of getting the wrong answer, because man, it sucks. But, well, let's just go for it. All these are W, so forget the weight 1. So we have this weight times the distance from this hinge. The distance is 0. Cool. Next one. We have a weight, and its distance, we're just going to say is L divided by 2. Cool. And then we have the third one. We have a weight, and its distance is leveraged out L. Cool. And then we're just going to divide it by the total mass, because that's what this person that signed up is going to be. His mass, you know what I mean, I guess it's him, is equal to these 3 masses. So, you know what I mean? They weigh a person. They make 3 masses that are, when you add them, are equal to the weight. You put that on a scale, you do this contest, sweet. And then so those weights are 3W. Okay, and now let's see what we have. So this is 0. This is 1/2 WL. So this is 1/2 WL plus WL. It's really good to change this into fractions where your denominators are the same. So 1 WL is 2 over 2 WL. And now I have the denominators are the same. You can use this term I just call oranges. This is 1 orange plus 2 oranges. Where like, hell yeah, this kind of whole thing you would just consider oranges, and we just have 1 plus 2. So mentally I can just see that's 3, and I think that's pretty easy. So we have 3 WL divided by 3W. Yeah, and are we doing this right? I feel like I messed up. Yeah. Oh, yeah, don't do the oranges thing. Or, I mean, don't explain it like I just did. Because you can't forget your denominator. You know what I mean? Cool, I have 3 oranges, but what the hell is an orange? You know, so we can do this 3 thing. But an orange is divide by 2 and then multiply by W times L. You know what I mean? So that's... So, yeah, let's... This comes up a lot when you have stuff like... the square root of 3 divided by 4 plus 2 square root 3. How the hell do you add these? Well, you got to get your denominators the same. So this is going to be 8 divided by 4 square root 3. And this is square root 3 divided by... And even throw a 1. This is 1/4. So we got 1/4 divided by 8/4. So this is going to be 9 square root 3 divided by 4. And so, you know, I would call these the oranges, and you have 1 orange plus 8 orange. Especially when you're doing a lot of heady stuff like this, just be like, hey, this is just 1 plus 8. But now I see where I'm making errors because it's really easy for me to drop that denominator. Okay, sweet. So we have 3 halves, but I knew my error right away because 3 divided by 3, I know the center is going to be, center of mass has got to be somewhere logical. And, you know what I mean? Well, let's find out where it is. So we have 3 halves WL. That's when we add these. And then we're going to divide by 3W. W's cancel, the 3's cancel, and we have L divided by 2. And see, I just don't believe this one. It seems bizarre when I do it like this. It seems like the center of mass is going to be somewhere over there. But it's not, because it will be. If I just said this was 2 times the mass, so let's do that. If I place 2 masses on here, and then the guy doing the contest only weighs two times the weight, you know what I mean? These are W's. And the guy weighs 2 times the weight. Let's do that one. So the distance will be, this first one is a W times L divided by 2. That's the distance. The second one is a W times L divided by the total weight, which is just 2 times W. And again, we have 1/2 plus 1. That's going to be 3/2 WL divided by 2W. W's cancel. This 2 pops downstairs, so we have 3/4 L. And that's what we would see if I just had these 2 masses. So that's so crazy that you have like 2 different scenarios. All right, and that was the aha moment for me, because I've always known this was a hinge. But what happens with this scenario, so if I just have both these weights, is when I balance it right here with 2W upwards from this dude hanging and winning the car, what happens there is that this hinge, this pivot, has no bearing load on it whatsoever. So it's just like if I have a lightweight foam plank with heavy weights, 2 heavy weights that are half this guy's weight, this guy is going to want to hook in the rope right here, go over the pulley, and then harness himself in. And now this, it's, you know, you're still having a plank on a hinge, and this is maybe the red herring. Is that what they say? You know, kind of like the, hey, this is probably going to get you maybe. But anyway, because like you think this hinge is like part of the deal. Where, no, you just actually want to balance this thing. So this would be kind of a very cool experiment with a foam plank. It's really hard to get a massless plank. But yeah, there you go. So, so booyah. And what you could do is you could show at the very beginning that you have a pulley right in the center of this plank, because the plank's got to have some sort of mass, and you could have it totally balanced where this plank is just balancing and where this pivot is visually rattling. You know what I mean? So you can just imagine that. If I have a plank, even though it's on a pivot, doesn't mean there has to be any force over there. I'm just like physically dangling the plank from the center. So yeah, so that's the huge difference between, well, if I have this weight in the center, why not just put the force over here and share it over here? Well, sure. But when it comes to center of mass, what you're doing is like, hey, if I just have this plank in outer space, that I'm applying a force on it here, and I'm only given one shot, you could go Hamilton or Eminem on that one. But so cliche. But anyway, so if I'm only given one force and a distance that I can apply that force, and that force is equal to the weight being loaded on this beam, just floating in outer space, I have to choose that distance. So that's what we're up against. So that's the definition of center of mass and center of area. All right, hell yeah. So let's try some of these. Hopefully we don't strike out too much. But I'm going to do two squares there. And then I'm going to go, let's see. I'm going to go 4, and I'm going to go 2 squares here. And then I'm going to go, so this is 0, 1, 2, 3, 4, 5, 6, 7, 8. And then over here I'm going to go 2 squares. So hell yeah. So each of these, so going back to this problem, man, we're running out of juice. Alright, hell yeah. So going back to this problem, making these panels a weight of 1 pound is exactly what I'm doing here. So I have this imaginary hinge, and then these are the weights, you know what I mean? And then they're on a foam, you know, same concept. This is a foam imaginary foam plank. It's hinged here. We still have that big old hinges. And then what, so the game show shows up and it's like, hey, you have to apply a force. And these are all 1 pound. 1, 2, 3, 4, 5, 6. 6 pounds. And you're given a 6 pound chunk of mass. And, and then into the page, these have thickness, right? Just so you can kind of see. And then they're on a plank. Anyway, so you're given a mass of 6 pounds. And you are, and sorry, this is all just downward. So you are going to have to hook it in somewhere along here. And it's going to go up and over a pulley. And then that chunk of mass is going to hang down. That's that 6 weight. And what we have to see is that this thing doesn't fly this way, and you didn't apply it in a horrible position where this weight down here leverages it down. If we see no movement, then you win the car. But crazy enough, if you see no movement, there is no force over here. And that's kind of by design, because if I said, hey, I have this plank that weighs W, and then I say that you are going to put an upwards force of W, and then over at the hinge there's some sort of extra number. Well, the forces in the Y direction do not balance, and this thing has to be traveling somehow upward, if that's the case. But more likely the opposite is true. Like if you thought you were just going to apply a W divided by 2 at this point, well, there's too much force down. This hinge must be making it up, because if we're seeing no motion, then this hinge has to be balancing. But even here, we might not be seeing. And that's the thing with motion. If I'm actually setting this as my pivot, I am going to see motion, because we have a net torque in this direction, because this weight kind of overpowers this weight, and you should have put this over here. If you were going to use the pin, put your weight divided by 2. But this whole idea of center of area and center of mass is the game show where if these are the weights involved, hey, you get to place one weight somewhere to balance all this. And so, yeah, let's do this one. So we're going to, and let's change it up. This is going to be the X direction, and we need to know where this X, and I guess, well, I don't know this symbol. It's just where the centroid is. The mean? Yeah, it's kind of the mean, I guess, between, yeah, it's literally, this symbol is the definition of this equation. So I guess I should reference that. And so let's do that equation. So we're going to have the sum of the weights times their distance. And see how this equation, we can say it's not area, it's weight. You know what I mean? And cool. And you could say it's not area, it's volume. You could do the same thing, volume times the distance divided by the total volume. Alright, so yeah, let's do this. So we have, okay, so we have, and we're going to use the idea that, hey, look at this. This is 2 times the weight, and its center is right there. So that itself is an integration process, but that's going to be for the third video. So the second video is just, hey, let's just use this equation and burn and get the right answer. And then the third video is the student wanted me to use integration techniques. And integration, I mean, it's going to vary. I mean, are you going to set your XY axis here? Are you going to use a differential area dA? Are you going to just use slices? Because he was into using slices, where I'm going to show that it's, I don't know, for me, I can't, I need to start with a differential area, like a point. If I'm doing integration, because the whole idea of integration is starting with some sort of thing that has no dimension, and then first giving it dimension. Like, hey, a differential dimension in this length, and yeah, then integrate from there to there, and then you got a length. Once you got a length, hell yeah, then you can, get an area. Once you got an area, you go to the other direction and get a volume. But it's just, I think you're missing out if you start the integration process from already having a slice. And I think it's very useful from a fundamental perspective is to start the integration process with a point. And a point could just be like, hey, I'm going to turn that point into some sort of differential length. I'm going to turn that point into a differential area. But even if you turn it into a differential area, you had to first turn it into a differential length, and then, you know what I mean, get a slice and then have it a differential area. So I don't know. I swear having a dx, dy, dz, I think that can be very heady. That's why people probably want to start with a slice. Okay, but hell yeah. So this is just doing it from kind of that intuition perspective of being like, well, if I did the integration of this, this would be the weight, and its center, its leverage arm would be right in the center, because that's what we're trying to figure out. This is the hinge, and then this weight is leveraged about this hinge. So this block is leveraged that distance. So yeah, let's do this so we can actually. Alright, I almost ran an SD card. Alright, booyah. But we're going to take a look at those two boxes, and we'll kind of blow it up a little bit. So there's box 1, there's box 2, here's our hinge, and these both have a weight. And we're going to use this equation, the center of this. We want to know the center in the x direction. And that equation is going to be the summation of the weights times their center divided by the summation of all the weights. And so we have this weight, that's going to be a W. It's at a distance, and we're just going to say these have distance of 1. And, or we do some variables. We call this box has side A, you know what I mean? So we have a weight of W, and then we have a distance of 1/2 A. Cool. Now on to the next one. We're summing this one. This one has a weight of W, and its distance is 1A plus 1/2 of A. That's going to be 3/2 A. So we have 3/2 A. And then we're going to divide by the total weight. That's going to be 2W. And so we see that we have 1/2 plus 3/2. That's going to be 4/2 or 2. So on the top we're going to have 2WA. On the bottom we have 2W. The two W's cancel, and we have the center is A. So there you go. So I think that is the hardest process to see, like, hey, if I have a very simple shape, like a rectangle. Same thing with a rectangle that's like this. If this has side 2A, and I want to find the center of that, it's the same thing, you know what I mean? You have the center of area, times that distance divided by the summation of the areas. If I'm saying this area, it's the same thing we just did. So I'm not going to go over that, but hell yeah, and then you get the center. Okay, so now let's hone in on this. So here's our equation, and we're going to do it. So we're going to say this is 2W, and it's at a distance, a leverage of 1. Cool. Next one is 2W. Its leverage arm is 4. Cool. And then we have 2 times the weight out here. Its leverage arm is 8. All right, and then we're going to divide by the total weight. We have 6 of these, 6 times W. And so this is 2. This is going to be 8W. This is going to be 16W. So we have 10, 26. So we're going to have 26W divided by 6W. That's going to be 13 thirds. Hell yeah. So x is 13 thirds. I don't know what that is, but I'd know that 12. I could do, this is going to be 12 thirds plus 1/3. 12 is going to be 3 times 4. What am I doing? Oh yeah, divided by 3 plus 1/3. 3's cancel, and this is going to be 4 plus 1/3. So hell yeah, 13 thirds. You know what I mean? It's going to be 4 plus 1/3. So just visually, I can come in here and be like 4 plus 1/3. So that's the center right there. So if I wanted to win the car, I would put this 6 on this pulley, and I would hook it right there. If there was just an infinite many hooks along this plank, along this game show, this is where I would hook it, and I would win the car. And so this would be a pretty cool game show to do, where you had like different shapes that weren't tricky, you know what I mean, like constant density materials that you could eyeball, and then your goal would be to pick the point that's going to balance the system from that perspective. But the highlight is that whatever weight is on that imaginary plank, this has to be equal to that. So these weigh 6, and that's that driving force. So essentially, what you're doing, well, I don't know. I think, yeah, I always thought it was just a, hey, hinge it out, and then you have these different masses, and, you know, you have to balance all those with 1. But I totally forgot that this hinge is irrelevant, because it's just the fact that, like, this came up today at the coffee, or this week at the coffee shop. The fact that you can sum moments, let's say summation of moments about this hinge 0 is 0. Well, the same thing is if you sum moments about the center of mass. Summing the moments about that point that you found is 0. Summing the moments, so if I sum the moments about 0.9, the summation of the moments, yeah, isn't that hella trippy? It's just like, I don't believe it. You know what I mean? So let's do that. So we're going to sum the moments about 0.9 right there. And that's going to equal 0. And you're just like, how the hell? Okay, because, and sorry I don't have this hinge. We could make this where this hinge is just this way. And this is down. And then the game show says we're going to go over here. Sorry, I was just working into the board, but I was doing that because these problems are all into the board. You have to look at this area as some sort of like leverage to, and maybe this is dumb, you know what I mean, to actually take a datum, because we're going to prove that this datum is irrelevant. The fact that you chose this location as your hinge, totally irrelevant. You could have put the hinge here. You could put the hinge anywhere. And so that's what we're explaining, is that the hinge is representing where you have to have the summations of the moments due to the forces balance. And so yeah, this is wild. So from 0.9, and now this is going to be my hinge. No, like, what? Oh, so I have this force up, that's 6, and then all of these are going to be down 1. That's all we have. It's irrelevant the fact that there's a hinge here. And the whole idea behind this is that we're going to know that the reactions at this hinge are 0. And so, cool. Yep, and they have to be, because the whole game show was to have 6 weights that were along this board, and then you had a driving weight of 6 that you had to place somewhere and then balance. So hell yeah, so this is that weight of 6. Cool, so the summation of the moment from 9, let's just get this one out of the way. This is going to be an upward force, and we're going to say it's a negative 6, and its distance is going to be, what the hell did we even say? 13 thirds? It was going to be 13 thirds, which was 4 1/3. Cool, that's going to be balanced by each of these weights. And so this one's going to be a combination of a positive 2W, a distance of 1. This one's going to be a positive 2W, a distance of 1, 2, 3, 4, 5, a distance of 5. And then this one is going to be 2W, a distance of 1, 2, 3, 4, 5, 6, 7, 8, a distance of 8. So now we have 16W, we have 10W, we have 2W. And I feel like we're going to get the wrong answer. Why is that? Oh, yep, because this is wrong. This is wrong. Yeah, I'm glad I caught my error. So, yeah, if this is 4 1/3 this direction, well, we're going to have 9 minus 4 1/3. So if 4 1/3 is 13 thirteenths, and 9, we have to say, is 27. So we have 27 thirds minus 13 thirds. And so that's going to be 27 minus 13, that's going to be 14. So this distance is going to be 14 thirds. So hell yeah, so this distance right here is 14 thirds from this leverage point of 9. So we have this weight of 6 is going to be hooked in right there, is going to provide that torque about this point. It's going to provide that moment. Cool. And so this should balance. Let's see if it does. This is going to be 3 times 2. That cancels, and we get negative 28. And sorry about this. This is 6W, so we have a W right there. So this is negative 28W plus, and now these work out. This is going to be 18 plus 10, that's 28. So we have 28W. But yeah, so I'm just surprised. It's just like there's so many little things that you can explain with equations. And but yeah, the whole fact that summation of moments, if you have a system in equilibrium, the summation of the moments is going to be, and I can't even, you know what I mean? I guess the next question would be, if you have something that's not in equilibrium, is the summation of the moments always the same value? I mean, I wouldn't think so, but in this, if we have equilibrium, if we do not have any motion, the summation of the moments at any point is going to be 0. And that point can be anywhere. It can be anywhere in the universe, and it's going to be 0. So it's just fascinating, even taking the sum of the moments from a point that's outside of the system. All right, hell yeah. So let's try to finish this one up, and we're going to use that mass approach. And then for the second video, I'm just going to burn through and do it with the area. But if we use this mass approach, we got 1, 2, 3, 4, 5. 1, 2, 3. And then we have, so we have this shape. And we're gonna put our hinge here. We're gonna call all of these 1 pound. So we have to say that this is a pound. These are pounds. This one's not, though. You know what I mean? What would be the weight of this? Well, we're gonna say the weight of this is 1 pound, but its center is going to be at 1/3 that height. So we have so this is still 1 pound. Same thing here. We're going to do that same thing as like, hey, the leverage of this is 5 pounds, and its leverage point is right there. Cool. And then we have these distances of 120, 240. Hell yeah. And then these distances are also 120. Cool. All right, so let's do it from, and then this is the y direction. So we have y prime is equal to, we're going to do the summation of the weights, and then their distance in the y direction. And then divided by the total weight. Let's do this one. So we have a weight of 5. We have a distance of 240 plus 60. We have a distance of 300 millimeters. Cool. Done with this rectangle. Let's move on to this rectangle. We have a weight of 2. We have a distance of 120. 120. Cool. And then we have these two. So let's just do one of them. We have a weight of 1. And then we have a distance of 2/3, 240. Cool. So 240 is 12 times 2 times 10. 24 times 10. 12 is 3 times 4 times 2 times 10. 3's cancel. And hell yeah. I don't know why I'm doing mental math right now. But what? Yeah, the 3's cancel, and we got 4 times 4, 16. That's going to be 160. What am I doing? Oh, yeah. Anytime I do this, if I say that this is 12 times 2 times 10, I really need to cross this out and just use that. And then if I say 12 is 3 times 4, cross out the 12. See, that's where I'm running into errors in my mental math. So now we have 2 times 2, 16. So this is going to be 160. So 2/3 of 240 is just 160. I don't know. That shouldn't have been that hard. I guess it was, though. Yeah, 24 divided by 3 is 8. And then 2 of those is 16. Holy Toledo. That was awful. Anyway, so we have that weight times that distance of 160. And then, so that's this weight of 1 times the distance of 160. And we're going to have that same thing over here. So I'm just going to do plus another 160. It's just going to be this twice. Divided by the total weight, 1, 2, 3, 4, 5, 6, 7, 8, 9. Hell yeah. And sweet, so we have 1500, we got 240, and then we have, this is going to be, what, 32. 40 plus 20 is 60, so we have 560. And then we're going to have 2060 divided by 9. Alright, 2000, see, I probably made a mistake, but nope, we didn't. We got it right. So our distance is 228.8 millimeters. And hell yeah. So we got the right answer. Not even using this equation where we have the summation of the areas and then the total area. Because what we did is we took these areas and said, well, hey, maybe they're made out of steel and they have some weight to them. And I'm just going to give them this nominal weight. I'm going to hinge it here. And I think, like, I always thought that was a brilliant idea. But now I'm realizing it's like when you do that, and if this is down into the page, and then you go to support this with a weight of 9 pounds. If this weighs 9 pounds, and you are given the task of saying, I'm going to take a weight that's equivalent to 9 pounds, but I need to place it somewhere in this direction. And we know it has to be placed in the center, but this y prime height is this 228. And so visibly, it's easy to, well, and I guess, I don't know, yeah, the hinge kind of messes it up, and I'm glad I talked my way through that, because if we do have this shape, and you do apply a force, and this thing does weigh, this hinge won't have any weight on it. So I'm really glad I thought of the idea of having a hinge with weld out holes where that pin is just rattling around. The second you put this 9 pounds up on this whole plate system that weighs 9 pounds in this shape, and you did it at that distance of this, if this is 240, then you did it at 228.8. This thing is just going to be perfectly balanced. So maybe, you know what I mean? But I still like to think of it as being hinged instead of just being balanced. I mean, I don't know. Because the hinge is where you're going to be taking your datum from and your moments from. It just happens to be that you're applying a force in the upward direction that's equal to the weight of this thing. And so there can't be any reaction in the y direction from this pin because these forces have to balance the weight of this down. And the reason why we use weights is because, I mean, the reason why I like to think of the center of area as, you know, the center of mass, of something with that area shape just being thin steel. One is because steel is heavy, and I can imagine it being very thin without much volume. And so it's technically, it could be considered an area. And it just gives you an idea of what's going on. And then what came from that, though, is this revelation that, well, obviously the pin has no, you are balancing it. At that point, if you're applying this force equally in this direction and at that location y prime, you know what I mean? And this would be the distance x prime if you took some other datum, is that that's the perfect point to balance that. And then just know that this value is going to change wherever you put your hinge. And the hinge is irrelevant. If I put the hinge here, you know, and said, where am I need to, you know, keeping this thing? One, from rotating about this hinge. But the take-home point is that I'm applying a force that's equal to the weight of that shape. And that's the same thing as saying, hey, this shape has an area. I'm applying an area that's the same area as this area. You know what I mean? So I just think it's way easier to think of as forces. But yeah, thinking of things as area having some sort of leverage is bizarre. You know what I mean? To say like, hey, if I have an axis here, this area has, I can consider this area a vector, and it has some sort of leverage from this distance. So this is y1, and this is area 1. This is area 2. This is the distance y2. And so, and we've already gone over the fact that it's a linear approach. So you can get away with not integrating in this direction. We can just say, hey, that square chunk of area is effectively if all the area was right there. So if you could squeeze all the area right there, which makes no sense either, where if it comes to masses, hell yeah, you know what I mean, you can take this shape and then just say, hey, I'm going to take little very heavy chunks of like cylindrical steel, spherical steel balls, and then with the lightweight rods, you know, kind of hook them all together with a very lightweight frame. And still, the same problem is you're going to have to balance this with the force that's going to be equal to all of those. So that force is equal to this whole system. And this system, these weights are there. So that is also how the fact that this is a first moment of area where you have this equation is the summation of area times that distance divided by the area. This is the leverage of area. And because it's a linear, kind of a linear relationship, it's not like the area times the distance squared. It just has this nice property that if I can take very geometric shapes and say, hey, this area is essentially if all the area was right at that location. And that's what we're doing with every problem, every beam that you come across. And that's the horrible part about just like simplifying these things too much and just getting used to it. Because I definitely graduated with not really caring about simple integrals. And I think sometimes the simple ones are the hardest. If I say this beam has a weight right there, that's wrong. I mean, it's a mathematical, whatever I'm just trying to say. I can't say that. But simplification, because the weight isn't there. The weight is everywhere, equally distributed. It's just the fact that if it's right in the center, hey, I'm going to have to support this beam. Two people are going to have to carry this beam, and they're going to equally have to share the weight. You know what I mean? So it's not that the weight is, the weight definitely ain't over there, and the weight, you know what I mean, ain't over there. But that's what you're doing is you would have to have a massless beam, and then you would have to have a pinpoint in the universe that just had like weight to it, and that's what we're doing. You know what I mean? So that actually seems more bizarro, but it's just fascinating how we just get so used to like drawing a beam and saying, oh, the weight's in the center, and so hell yeah. You know what I mean? Growing your intuition is a slow process, and I don't mind doing it in these videos, because I definitely did it today. Is just like, hey, I think I have a misunderstanding of something, and so let's explore that. And I think that's a very difficult thing to do, because it's really easy to be like, ooh, I don't think I understand that fully. Let me just ignore it, and for sure not talk about it in the moment. But I think the faster that you can, like, hey, like, is something going on at this hinge? Whoa, that hinge has no force, and fundamentally it doesn't. In engineering, you got like kind of three different, I don't know why I'm saying three, but definitely two. You have equations that are, you know, well, and then sometimes equations are awful too, because equations might only be limited, and you don't know that. So like, here's an equation for something, and you're like, hey, it's limited. It might be limited in its scope, in its application. You know what I mean? Like this whole idea of saying the weight's going to be in the center of a beam. Well, and then when you get something like this, a beam that looks like this, is like, holy hell, now you're just freaking out. You know what I mean? Or if you get a beam, yeah, I don't know. You know what I mean? Let's say you get a bridge section that looks like this, and you're just like, nope, I did not ask for that. You know what I mean? I don't know where the center of the weight is no more. And I think that's a disservice. And even taking a rectangle and just saying it's a third and 2/3 is just like it's just fascinating how, and I'll speak for myself, when I don't understand the integration at the simplest level, where most people, yeah, they know if this is like an upside down, if this is y is equal to negative x squared, hell yeah, and that's the shape. Is like, oh, people could find the center of that all day. Like, why is that the case? Why, when you have something that's requires integration, where you can see the power rule like right off of the bat, why is that more intuitive than just saying, hey, something super basic, like what's the integration of this? What's the integration of this? And that's what we're going to kind of explore in the next 3 videos. Because the next video is just going to be, hey, let's just use this equation and crush out this answer. And then we can start doing integration. Because when we do the integration, hey, we might mess up where we need to use this answer as a reference point. So sweet, I'm going to be done with this one. This was pretty good. Kind of intuition with centers, centroids, centers of area. And same as associated with centers of mass if you give it some sort of volume and density. All right, booyah.